Welcome back. In this episode, we're looking at a pool that we're filling up with a hose. It's a nice summer day. We're filling up the pool here so we can go swimming. We are asked, how long would it take to fill up a pool, and I'll explain the pool's dimensions and the hose's dimensions in just a second, to 1.1 meters. Simple question. The diameter of the pool is 7.5 meters across, and the diameter of the hose's output cross-sectional area of that is 5/8 inches. We're told that the velocity of which the water is exiting the hose is 0.5 meters a second. Okay, so we are also told, and we're not given this in the problem, but it's important information to help us solve the problem, is that the volume of the cylinder, of a cylinder, not the cylinder, which is what this is here, the pool, is going to be pi r squared times the height. Okay, and then we are also told that 1 meter is equal to 39.4 inches, just a helpful conversion. Okay, so before I get into any solving, I want to first identify a relationship I could make among our variables to help us solve for that time interval that it would take to fill up the pool. So we know that there's a fixed volume for the pool, right? And this is how I went about solving this. There's a fixed volume for the pool, and we're filling it up with some rate, right? A flow rate. A flow rate is meters cubed per second, right? So in my head I thought, okay, well, if I have some flow rate, right, I'm adding some volume per unit time to a pool, for example. Well, if I multiply that by a factor of time, that's going to give me a snapshot of the volume that I have at that point. So if I fill up the pool for 5 seconds, there's going to be 5 seconds of flow rate, and therefore 5 seconds of a volume, right? That's going to come out of that. But if I go 10 seconds, that overall volume is going to double. And if I triple the amount of time, right, it's going to triple the amount of volume that we have. So we can say that the flow rate times the delta T, that change in time, is going to be equal to the volume. Okay, so we're flowing something in over an amount of time that's going to give us volume. And if you don't believe me, look at the units. I mean, flow rate is just a unit of volume, so we'll say a meter cubed in this case, and that's what we're actually going to use per second, for example. And let's say 15 seconds, so we have seconds on the top over nothing, okay? And I'll just erase that not to confuse you. We notice that the seconds are going to cancel, and we're left with meters cubed. That's exactly what volume is, meters cubed. Okay, so let's use this here. Let's use this idea to solve for our delta T. It requires us to know the flow rate and the volume, and that's where some of the math can come in. So let's find the volume. We need to find the volume of the pool. Okay, the volume of the pool overall, and we're not given the time, but we're given a flow rate. Given some flow rate, what is our volume, right? So we're told that the volume of a cylinder is equal to pi r squared h, right? We're given the height, but we're only given the diameter. Now, diameter is 1/2 height, so let's actually just go ahead and divide this by 2 to give us a radius. 3.75 meters for a radius. Okay, so given that, we have 3.75 meters of a radius, and we have 1.1 meters of a height. We can solve for the volume of the cylinder, so let's go ahead and do that. We're just going to simply plug in pi times r squared, 3.75 squared, and then we're going to multiply that by our height, 1.1. We're going to find that the volume of that pool is 48.6 meters cubed. Okay, that's a pretty sizable volume. That could make for a very fun summer day. We do not know the time interval of which we are doing this in, but if we calculate the flow rate, we can divide it and get that, okay? So let's go ahead and do that. Flow rate is equal to the cross-sectional area of which the fluid is leaving, times, and that's going to be the velocity of which the particles are leaving. We have both, believe it or not. The velocity of which the water is leaving and going into the pool, we're given that velocity, right? That's 0.5 meters per second. Okay, so we have the velocity. Now we just need to find the cross-sectional area of the hose, right? Because all the particles are leaving that confined area at one point. That will give us a flow rate of a volume per unit time. So let's go ahead and calculate that. It's a little tricky here because we're given in inches. So we have to do a little conversion. 5 over 8 inches. We'll just do a little bit of dimensional analysis. 39.4 inches over 1 meter. So we can actually find the amount of meters that we have for the diameter. So let's go ahead and do that. 5 over 8 divided by 39.4. We're going to find that our diameter in terms of meters is 0.0159. Are we done yet? Are we able to plug this into the area of a circle formula, which is pi r squared? Are we allowed to do that yet? No, we're not, because this is a diameter. We're asked to find a radius so we can find the area of a circle. Okay, so let's just divide it by 2. Let's see what we get. We are going to get 0.0079, and we'll keep it consistent. This is our radius. Our radius is equal to 0.00793 meters. Now we can find the area of that circle. We just have to plug it in, the radius into here, right? So let's go ahead and do that. Pi times our radius, 0.00793, squared. Okay, we're going to find that the cross-sectional area of that hose is equal to, and I'm going to put this in scientific notation. Please review that if you are not familiar with scientific notation, but 1.98 times 10 to the negative 4 meters squared is going to be our cross-sectional area. Now we can go ahead and plug that in with our velocity to get a flow rate. So let's actually set that up, 9.8 times 10 to the negative 4 meters squared. Notice, it's meters squared times a meter over a second. So that's going to give us meters to the third over seconds. Does it make sense? All right, moving on. So let's just plug and chug here for our velocity, or our flow rate. And we're going to find the flow rate is going to be a really weird number. And this might make you anxious. When I get weird numbers like this, I'm like, that doesn't seem right. But let's thug it out here. Okay, and this will be meters cubed per second. Okay, but here's where it becomes interesting. Meters cubed a second, that hose cross-sectional area is not very big. So we would expect the flow rate to be very, very small. When we divide it over, we're going to see it's going to take a lot of time in seconds to reach that. So let's go ahead and do that. We're going to take our 48.6 meters cubed. We're going to divide that by 9.88 times 10 to the 5th. Okay, and we're going to find that, to the negative 5th. And we're going to find that delta T is equal to big number, 491,903 seconds. So it takes that much time in seconds just to fill this pool's volume up to a height of 1.1 meters. But I don't really like the way that that's given. I want to put it in like, it's not just like, oh, if I asked your neighbor, okay, I need you to fill up my pool. Can you fill it for exactly 491,903 seconds? No, you'd say, oh, you need to fill it for this amount of hours. Could you go walk your dog, go out to the movies, come back, and take the hose out? Okay, that's what you would say. So how do you convert that? Well, we just do a little bit of dimensional analysis, and we will get an answer. So let's just convert it, and let's see what we get every step of the way until it's a unit that is logical to tell someone. So we know that there's 60 seconds in every minute, and I know that the minutes is going to be large because this number will just reduce by 1 power given that it's divided by 10. Okay, so we know that there's 60 minutes in an hour. Okay, so now we're going to be in about thousands of hours. Now let's say that there's 24 hours per day. Okay, so how many days would it take? I think that's a good place to stop, right? If you went on vacation and you told them to fill your pool up, your neighbor, for example, to fill your pool up, okay, come back in this amount of days, in this amount of hours, please. Okay, that's a little bit better, I would say, to tell your neighbor so you don't look crazy, right? But who really does these calculations? You kind of just do it when you want to for a physics class and nothing else. So we would calculate that it would take 5.69 whole days to fill the pool with that little itty bitty hose up to that height, given the volume of which we are given for that pool. What a problem that was. Quite a fun one. And this isn't really a given formula. You kind of have to think through it to kind of understand how you get there. Took me a little bit, but when I understood, I was like, okay, yep, makes sense. Hope you guys enjoyed. If you did, please drop a like, comment if you have any questions, and subscribe, please. Have a wonderful day.